Hey everybody, we're going to go ahead and work through all of the problems on these heat of reaction questions. So here we go. First question, compute the heat of reaction for the formation of 193 grams of ammonium bromide from ammonia and hydrogen bromide. Okay, so basically for this kind of thing, we just need to set ourselves up some calculations. So we have, we're going to need molar mass, and so our molar mass is going to come from 14 grams for the nitrogen, plus 4 times 1 for the hydrogen, plus the molar mass for the bromine, which is going to be rounds basically to 80. And let me just check that real quick and make sure that I am looking at the right thing. Yes, it basically rounds to 80. So then that means that our molar mass is 9498 is going to be our molar mass. Okay, so if we have 193 grams of NH4Br, then we're going to be able to first convert that to moles by dividing by 98 grams per 1 mole of ammonium bromide. And then we're going to be able to convert that, boy, I'm erasing everything. Then we're going to be able to convert that to kilojoules, remembering that the kilojoules are given per, in this case, 1 mole of ammonium bromide. Because when you look at this, this is already a balanced equation here. So we have 1 mole of ammonium bromide produces negative 188.32 kilojoules. So then it's just a matter of multiplying and dividing, and you're going to see that this kind of thing actually just happens over and over and over again in the same format. And yes, I'm trying to talk while I am calculating, so we all know how that goes. So I end up with negative 370.9 kilojoules for our value for the amount of heat that is produced. Okay, so for the next one, we are given 0.772 grams of cobalt-2 carbonate, and we want to know, well, what is the total amount of heat that is used in the reaction. Please note that since this one was negative, that means that this was exothermic, and since this one is positive, that is endothermic. Okay, so for this one, heat is going to be used, and so I have 0.772 grams of cobalt-2 carbonate, and I am going to have to calculate a molar mass. So my molar mass is going to be cobalt, which is 63.5, plus carbonate, which is carbon plus 3 oxygens, which is 48. So that means we should have, and let me do my math real quick because we all know, plus 63.5 plus 60. I know I should be able to do that in my head, but I couldn't do it. 123.5 is my molar mass. So I'm going to divide this by 123.5 grams, and that's per 1 mole of cobalt-2 carbonate. And then for every 1 mole of cobalt-2 carbonate that is decomposed, we are going to have a positive 81.6 kilojoules of heat used up. So when we do our math, 0.772 divided by 123.5 times 81.6, we get 0.510 kilojoules that is going to be used. If we wanted to convert that into joules, we could say 510 joules. Nothing said that we have to, but we could do that. Okay, I'm going to go ahead and complete the calculations for the next two so that you can see how those work out, but it should be pretty much the same thing over and over again. Okay, so taking a look at what all we have there. For number 3, that was an exothermic reaction because we had a negative value in the delta H. So that tells us that that is an exothermic reaction. And so we're able to calculate exactly how much kilojoules is evolved or produced in that reaction. Then for number 4, things changed just a little bit. Instead, we are starting with kilojoules, and it said energy is released, and that's telling us that in fact that is an exothermic reaction, and so that must come out, that must be a negative number. So cool. That also tells us just by that it's also exothermic as well. So we're going to start with what we are given, and I made it negative because I want my 2 negatives to cancel out, and we know that heat was released. So negative. So I start with that. I know that for every 1 mole of CrO3 that is reacted, I'm going to evolve 5.4 kilojoules, and then I found my molar mass to be 100. So I was able to calculate 114 grams of CrO3, excuse me. So then we have number 5. Number 5 was back to the grams situation, but the thing that changed about number 5 was that our value for the number of moles of Fe2O3 was actually not 1. And in that case, we were going to have to divide by 2 to get our correct answer. So we end up with the multiplication, and I'm looking at my multiplication wondering if I got it right. So let me do 560.4 times 17.1, and then I'm going to divide that by 2 and divide it by 159.7, because I don't think, well, 30 is what I'm coming out with. I was second guessing myself there. Always check your work when you're doing these. Okay, so then for number 6, what is the change in heat that occurs when 1.24 grams of NO reacts as in the following reaction? I need to make sure that I get my molar mass of 14.16, so that's going to equal 30 grams per mole, because I'm going to need that value. So I'm going to set up my problem. I'm given 1.24 grams of NO, and I'm going to go ahead and convert that to moles using 30 grams for every 1 mole of NO. And then I'm going to use my mole ratio, and I have 2 moles of NO for every, and this is exothermic because this is on the product, for every negative 114.14 kilojoules that is produced. And then we can go ahead and do the math there. 1.24 times negative 114.14 divided by 2, and then divided by 30 there. And so we end up with negative 2.36 kilojoules for our answer on that one. Okay. All right, let's go on to our next set here. Number 7, how much heat is transferred when 8.03 grams of carbon are combusted with oxygen? Okay, I'm going to do that work and show it to you. And then how much energy is transferred? I'm going to go ahead and do both of those and then come back and show you what those look like. Okay, so both of these were pretty straightforward, using our mole ratios as needed and using our molar masses as needed. We get the same turnaround kind of thing. Just make sure that you recognize when things are negative, those are exothermic. When the delta H is positive, that's endothermic. And I think that this is probably pretty straightforward. Okay, so let's go on and look at Hess's law. And what I'm going to do is I'm actually going to fix this so that it's all on one page. So I'm going to go ahead and do that and then move the page up here. Okay, so here we have a heat of reaction that is using these 3 reactions here. So calculate the energy absorbed when 68.7 grams of sodium bicarbonate is being decomposed. So sodium bicarbonate being decomposed is this reaction right here. So we want to be able to do that sort of math again. So I'm going to do 68.7 grams of NaHCO3, and I'm going to need to use my molar mass, which should be 23 plus 1 plus 12 plus 48. So 23 plus 1 plus 12 plus 48 is telling me that my molar mass is 84 grams for every 1 mole of sodium bicarbonate, and I have a mole ratio of 2 moles of sodium bicarbonate for 129, not 5, 29, there we go, kilojoules. And I can see that that is, the way that is set up, that is endothermic right there. So in doing that math, I have 68.7 divided by 84 times 129, and that's divided by 2. And so I end up with 52.8 kilojoules. All right. So then my next question is calculate the mass of calcium hydroxide. All right, calculate the mass of calcium hydroxide that can be formed using 742.9 kilojoules. Okay, so the mass of calcium hydroxide that can be formed is going to be talking about this reaction right here, and we're going to use 742.9 kilojoules. And by using the terminology using, we're going to assume that this is endothermic. And so that's going to be positive. And so I'm going to calculate that using the information I have in the problem, 65.2 kilojoules for every 1 mole. And I'm actually having only 1 mole in that balanced equation. So all I have to do is divide here 742.9 divided by 65.2. And so I'm getting, in moles, I would be getting 11.39 moles. So that's going to be moles of the calcium hydroxide, but I need mass. So I'm going to end up having to multiply the moles by calcium hydroxide's molar mass, and that's going to be 40 plus 2 times 1 for the hydrogen plus 2 times 16 for the oxygen. So that's 42 plus 32, and that's going to give me 74 grams per mole. And when I multiply that, I am going to end up with 843 kilojoules will be used in that reaction. Sorry, that won't be kilojoules, will it? It will be grams of CaOH2. Okay, and then calculate the energy released when 88.4 liters of carbon monoxide is reacted with excess iron 3 oxide. So there we have 88.4 liters of carbon monoxide, CO, is reacted with excess iron 3 oxide, and it's really not giving us much more information other than liters of carbon monoxide. And so what we have to figure out is simply a mole ratio. And so we're going to have to make an assumption with this problem, and that is that 22.7 moles per liter is going to be the molar volume that we're going to use, and because we don't have any information about pressure, temperature, and volume, we also don't have any information whether these are at standard conditions. So we're going to have to make an assumption here. So assuming that we have 22.7 moles, sorry, let's make sure we do that right, because we want to make sure we calculate correctly. Ooh, that is not what I wanted. Okay, so let me make sure that we recognize that the 22.7 is actually moles per, is actually written as liters per mole. Okay, so that means that, let me make sure that I change my perspective here so you guys can see a little bit more of what is going on here. There, and we're running out of space here, so I need, okay. So I'm stuck with that. Okay, so let me try to squeeze it down here at the bottom. So I'm going to have 22.7 liters for every 1 mole of gas. And so then we, now that we know moles and we've converted to moles, then we can use the 26.3 kilojoules for every 1 mole. So that means for every 1 mole of this gas, we are going to produce 26.3 kilojoules of heat. So that makes that a negative number because it's on the product side of the reaction. So we're going to have 88.4 divided by 22.7, and we're going to multiply that by negative 26.3. 3, and so we're going to end up with negative 102 kilojoules will be produced there. Okay, so in going back, let's go back to this overall. What if we had to take a look at these? I'm not sure why this was labeled Hess's law, because none of these are actually related to each other as a additional Hess's law sort of thing. So I don't think that this was a good example of Hess's law. I think that this was just more moles calculations. Okay, everybody, let's go ahead and move on to the next part. Heat of formation, and you're going to be using information from your IB Chem data booklet. So it says, using the standard heats of formation found in your data booklet, write a balanced equation and calculate the heat of reaction for hydrogen peroxide reacting with nitrogen monoxide to form steam and nitrogen dioxide. So we have a chemical reaction of hydrogen peroxide, H2O2, reacting with nitrogen monoxide, which is NO, to form steam, which you guys should know is water. And let's make sure everybody knows that's going to be in gaseous form, plus some nitrogen dioxide. So what we're going to want to do first is balance this thing and make sure that it's all balanced. So I have 2 hydrogens, 3 oxygens, 1 nitrogen. So it's all balanced. So now we need to go look for the information we need for each of these in our chemistry data booklet, and we're going to use heats of formation. So let's go ahead and navigate to our chemistry data booklet and see what we can find. And so I'm going to scroll here and find our heats of formation. You can see all kinds of information. I'm going to go past the periodic tables, and those are bond lengths, so we don't need bond lengths. And then we are going to bond enthalpies. We are not using bond enthalpies for this, so keep that in mind. We're not using bond enthalpies for this. So we need to go on thermodynamic data, and you'll notice right here it does say heats of formation. So the question really is do we have the right information on the data booklet to be able to answer this question? So that's what we're trying to do here. And we needed some hydrogen peroxide, we needed some nitrogen monoxide, and some gaseous water, and some nitrogen dioxide. So let's just see what we have here. And I've got to get that working. So I also want to make this bigger because this is really hard to see. So we're going to get this bigger so we can see it. So here we go. Let's take a look here. Looking down here, I'm not sure if the data booklet, I do see steam. I do see carbon monoxide, but I don't see nitrogen monoxide, enthalpies of combustion. That's not going to be what we need there. So it doesn't look like our data booklet is going to be very useful in this format. So what I'm going to do is navigate to a different source to find heats of formation so that we can complete our problem here. So heats of formation, we really need to have standard enthalpies of formation. Let's see if we can find an image that has a good set here for us to look at. Let's go look at this example here. Do we have nitrogens? It does look like we have nitrogens. Do we have hydrogen peroxide? We do have some hydrogen peroxide. Okay, so this is going to be a very lovely source here. Let's go see if we can get that thing to be bigger. We're going to go with bigger here. And bigger. Okay, so all I've done so far is I've gone and I've tried to find a heat of formation source. So what I'm going to do is I'm going to copy and paste this into my, I'm going to copy this and paste it into my heats of formation reaction worksheet, so I have it to look at here. So I'm going to go ahead and paste that right there so we have it to look at and we can respond with the correct things. Okay, so using standard heats of formation. That terminology, standard heats of formation, means at standard temperature and pressure. And so if you were to go look at this, it does tell you that concentration of aqueous solutions is 1 molar. Do you see this little symbol right here next to the HF? That is telling you that that is at standard conditions, which is 25 degrees Celsius and 1 atmosphere. And of course, all of these are 1 molar. So we are going to go ahead and use this information for our calculation. Okay, so remember please that our chemical reaction was H2O2 plus, let me make sure I'm writing, H2O2, oh boy. Come on, there we go. And there we go. So our reaction was, oh my goodness, you guys, the struggle is real here. All right, so let me try this again. There we go. H2O2 plus NO yielded some steam, which is H2O gas, and some NO2, which was nitrogen dioxide. Okay, so we need a heat of formation, and we are going to, and I'm going to go circle the things that we need. We need H2O2, this one here. I'm going to underline it because we can't read it otherwise. And we need some NO gas, so there's that there. And we need some NO2, there's that there. And we need some water vapor, which is that right there. And to do this math, we are also going to need to remember that we are doing heats of the products minus the heats of the reactants. And so our products are going to come first. So I'm going to do the water vapor first, which is negative 241.818. And I'm going to add to that the NO2, which is, and I've got to erase some of this because I can't see what I wrote here, which is 33.18. So 33.18. And so that is my products. And from that, I'm going to subtract my reactants. And my reactants were H2O2, which is negative 187.8. And to that, I'm going to add the value for the NO, which is 33.18. And it looks like I made a mistake over here because this one shouldn't have been 33.18. I looked at the wrong number. It should have been 80. Oh, I'm looking at all kinds of wrong numbers. Let's go back and make sure that N2O was correct as 33.18 and to NO2. That was correct. What was wrong was the NO, which should have been instead, reading my table correctly, should have been 90.25. Okay, so when I get this all done, my result should have come out to, and I got to get my math going on, negative 241.818 plus a 33.18, and from that I'm going to subtract negative 187.8 plus 90.25, and my overall comes out to negative 111.09, and that should be kilojoules per mole. Okay, so there is our first example there, and we did have to go find our information on a separate table because the data booklet in this case did not provide us the information we needed. Okay, so right now I am going to take and I'm going to cut this and move it down with us to the next part here because I need to be able to use it on the next example. And our next example says show a balanced equation and calculate the heat of reaction when sodium reacts with calcium carbonate in a single displacement reaction. I'm going to go ahead and do that math and then I will show you what. Okay, so for this next one, we had to write out the balanced equation. There's our single replacement reaction. I did go ahead and balance it, but we did not need to worry about that so much because we had two elements in our equation. And remember, those elements get a 0 for their their heat of formation because they form naturally in nature, and so we don't have a heat of formation for them. So instead, we're just going to do products minus reactants. We have no coefficients, so we're going to use negative 1130.7 for the heat of formation of sodium carbonate, minus negative 1206.9 for the heat of formation for calcium carbonate, and we came out with an overall 76.2 kilojoules per mole. And if we had to say, then we would say that this is overall an endothermic reaction because the kilojoules came out to be a positive number. Okay, so for this next one, we had to write out the chemical reaction, which was hydrogen sulfide, H2S, plus chlorine, which you have to remember is diatomic, so Cl2, yields monoclinic sulfur, that is just sulfur all by itself, and 2, because of balancing, HCl. Now, I happen to know that the hydrogen sulfide and the chlorine are both gases, so it is also going to form a gaseous HCl. And that's going to be important because when you look at the HCl, there's a couple of different HCls to choose. So as a result, we will choose the HCl that is the gaseous one. And a better written question would have told you that what the states of matter of everything were. So the first thing that we have to do is products minus reactants. So I do 2 times negative 92.307 for the HCl minus negative 20.63 for the H2S, and I get negative 163.98 kilojoules per mole. Okay, so now that I know that, now that I can do some stoichiometry of 657 grams of HCl divided by molar mass, because that gives us moles, and then divided by mole ratio, and which is equal to the negative 163.98. So I got negative 1,496 kilojoules, and in fact, this is actually exothermic if we had to say so. Okay, so both of these problems were given to you as Hess's law sorts of problems. So in the first one, everything was already in the right places and everything canceled out appropriately. So all I had to do is combine the two delta H's, making that one a pretty easy problem. In the next one, we had to do some stuff. We had to multiply both equations by 1/4. And we had to flip the second equation. So in doing that, multiplying both by 1/4, I multiplied both delta H's by 1/4. Then I made sure everything canceled out. And when I combined them, I got negative 66.75. For question 12, it says the standard enthalpy change of formation of Al2O3 solid is negative 1,669 kilojoules per mole. And the standard enthalpy change of formation of Fe2O3 solid is negative 822 kilojoules per mole. Use these values to calculate the standard heat of formation for the following reaction. So there's our following reaction, and I went ahead and wrote all over that so that you could see that, in fact, we were going to do products minus reactants, and I went ahead and did that and got negative 847 kilojoules per mole. Since it came out negative, this was exothermic. Okay, so this final reaction is based on the fact that that comes out to be exothermic. So draw an enthalpy level diagram means we're going to draw a graph. And so our graph is going to be energy on the x-axis and something called the reaction coordinate on the y-axis, and it's basically going to take us from the reactants to the products. So we're going to start at some random spot where the reactants are. We're going to assume there's a little bit of activation energy required, but since this was exothermic, our products have to come out lower than our reactants. And then we have to note, because it says state the conditions under which standard enthalpy changes are measured. So that is going to be 25 degrees Celsius, 1 atmosphere, and 1 molar solutions. And that should be the answer to this question right